Welcome to the Insightful Professor. Today we're going to discuss generics in the Java programming language. In an earlier video, we discussed recursion. And with recursion, we said one of the things that we do is we postpone processing. Let's consider an example of reversing the order of a sequence of characters. Suppose you receive the sequence of characters A, B, C, and they come to you in that order. What we'd like to do is print out the characters that we receive, but reverse the order so that the result of what we present will be CBA. So what we need to do is, as we receive the characters, we need to postpone the processing of the characters until we receive that very last character. Then and only then will we be able to start printing characters. So how did we postpone the processing? Well, what we did was we used the system stack. By using recursion, the system actually kind of takes a picture of the current state of the environment that you're running in, say the invoking routine, and puts that into suspension as it calls the subroutine that you're invoking. So it's not just with recursion, but it's with subroutine calls in general that the system employs something called a system stack. What happened was, as we received each of the characters and we said, well, I'm not ready to display this, I put it into effectively a stack frame by making a recursive call. So that stack frame had to be sufficient in size to accommodate effectively just a single character. However, what we want to look at is something more general. Whenever you call a subroutine, a stack frame comes into play. That stack frame is not necessarily going to be identical to the one that we used when we did the reverse character string. All we needed to store there was a single character, but very often we'll have local variables within the routine that is making the call, and we will need to take a snapshot or a picture of those, what we refer to as the current state of that system, the current state of the invoking routine. Because when we complete the subroutine call, we need to restore the environment to the way it was so that we can pick up where we left off. So again, a stack frame will come into play, but that stack frame will have to accommodate more than just a single character. So what we'd like to do with generics is discuss the idea of how to write some kind of an algorithm or write code that can employ a generalized solution. That's what this video is going to address. Well, in our example discussion, the stack frame was different. The processing was the same. There was a push operation that occurred to add a stack frame to the stack, and subsequently there was a pop operation to remove a stack frame from the stack. The thing that differed was not the processing, but what was processed. The nature or the structure of the stack frame in each case was different, but the processing was the same. That is the essence of generics, and that's what we're going to be looking at. In C++ and some other languages, these things are sometimes referred to as template functions or template classes. C++ has something called the STL, the standard template library, which uses some kind of generalized code predefined and available to us. In Java, they do it a little bit differently, and they name it a little bit differently. In Java, they refer to it as generics, or sometimes called parameterized classes. Let's take a look at an example. We want to see the effect of not using generics, which results in code duplication. By not duplicating code, we're able to avoid having multiple code bases, multiple versions of the same thing, even though we're working with essentially the same processing. This can be very expensive to maintain multiple code bases. So this is why if we could write it once and use it in many different ways, this would be much better. It's kind of a form of code reuse. Suppose we needed to create a class that could process integer data. Then we could do something where we say we don't need generics because we're always using integer data. So we would come up with something perhaps along this line. We create a class called intCell. It has this thing called stored value, which is of type integer. That's the value that's going to be stored and subsequently manipulated by the methods defined within the class. So notice throughout this block of code that what we see is the data type is int. The value stored is int. The constructor accepts an int. The getter and the setter each manipulate an int because we're working strictly with integer data. So that's fine, except suppose down the road we say, we'd like to be able to do the same thing, achieve the same functionality with floating point data. Then what would happen is we would need to write a separate, distinct class, effectively duplicating the functionality by rewriting the code, but changing the definition such that we were using double rather than integer. So now there would be two class definitions where the code was essentially the same. The only difference was the data type. We couldn't really reuse the code directly. We have to come up with a distinct definition of another class. And this would be true for any other data type that we would like to do similar processing with. So we could end up with several different class definitions, which effectively were all doing the same thing, but the definitions, the source code was different. So what we would like to do is to be able to write code one way, maintain one code base, and then be able to reuse that code for any kind of data. A generalized solution. That's what generics is all about. So here's an example where we would then use those cells that we defined. And notice we would say, I have an integer cell, and I write this code here. Then I would say I've got a double cell, I write this code here. And of course, this code relies on the existence of two distinct classes. With generic programming, we look at moving in a slightly different direction. We're going to write code that can work for many different types of data. The code is generic by using what we call a parameter as a placeholder. It's kind of like what we do when we write a method and we write formal parameters. When we write a method, we're describing with a formal parameter what type of thing we're expecting to receive as input. And when we call the method, we can pass it a whole bunch of different values provided they're of that type. But the point is that the method is of a generalized solution. It's expecting any integer or any double or any string and then operating on it so that when we pass the actual parameter, then we actually know what we're going to be working with. That's similar to what we're doing when we define a generic class or a parameterized type of class. What we do is we define a class that accepts these type parameters. Then when you give me one of the types, if you give me an integer or a double or a string, then I know what I'm operating on. So that's the idea of how the stack would work. The stack is going to be able to do push and pop regardless of what kind of thing you give it. It's a generalized solution. So we want to understand that notion as we develop our kind of generalized code. Now, a generic type is a generic class, or it could be an interface that is parameterized over types. So the class definition includes what we refer to as a type parameter. This is what serves as the placeholder. This is similar to the formal parameter that we define when we write a method. The type must be a reference type, not a primitive type. What that means is it effectively has to be a class. So I could pass something like string, but I could not follow with the example that we were using and pass a simple primitive data type like int or double or float. That would not be permitted. So I kind of misled you a little bit with the example, but there's a solution to that we'll talk about shortly, something called a wrapper class. And we'll introduce that and give you an explanation of that and show you that we still can accomplish our goal of creating some kind of a generic class that can support integer processing and double processing and so forth. So just hold on for that, and we'll continue with our discussion here. By convention, this type parameter is going to be something like T, a single letter. It's not required that it be a single letter, and it's not required that you use T. Our example will follow the convention, and we'll use a single parameter which consists of a single character, uppercase T. Any non-keyword identifier would work as a type parameter, and that'll become clearer as we go along. But just think about how you've named formal parameters in method headings. You've been able to call those formal parameters any name you wish. That's the same idea here. You could also have more than one type parameter. Obviously, the names must differ from one another if these two parameters or these multiple parameters exist within the same generic class. Once we've coded the class definition, and it's a generic class, then we're going to store that source code in a file and compile it the same way we would if it was just a regular class, not a template or generic type of class. So here's our example coming together. We're looking for that general solution where we're saying it's not going to work just for integer or just for double, but it can work for anything. So we define here the type parameter. So this type parameter is enclosed within the angle brackets. Again, it's similar to the idea of a formal parameter for a method. Then we use that type parameter throughout the code wherever we want that data type to apply. Remember, we had created an integer cell where we called it stored value, and the data type was int. We created a double cell where we had a variable called stored value, and it had a type of double. So the T, as shown here, is just a placeholder, and this will get filled in later on when we actually instantiate the generic class. Here we have the example that uses our generic cell. Notice we're saying cell, and then we use angle brackets once again, and this is almost like how we invoke the subroutine that we would call if it was a method and pass an actual parameter. So what we're doing is we're instantiating the generic class called cell, and we're passing integer, where integer will substitute for the T, and it will substitute throughout the code wherever that T appears. Then in the second case, we're instantiating this generic class using double. And we have a third example where we're using string. So again, any class will work. Now the trick here that allows us to get away with using integer and double is notice that these names begin with an uppercase letter, the same way string that you're familiar with begins with an uppercase letter, meaning that it is a class. Well, double and integer, as spelled out here and beginning with the uppercase letter, indicate it's a class. These are actually wrapper classes, and we'll explain those, as I said, a little bit later. We could not simply put int, double, float, char. We could not use any of the primitive data types. It would not work. We talked about the motivation for doing the generics. Let's look at something that kind of expands on that with the examples we've been discussing and see this in action. We were talking about the idea of the stack frame for the system stack, and we wanted it to be such that it could accommodate a single character if that's all we needed to push onto the stack, or it could accommodate a whole set of local variable values and a bunch of other things if necessary. That is, the structure of the stack frame could differ, but the functioning of pushing and popping would remain the same. So consider the situation where we wanted to reverse the sequence of characters. So what we would do is the user would enter, say, A, B, C in that order through a series of pushes, and we would subsequently pop, but we would pop in reverse order, getting the C, getting the B, getting the A. And that's where, after the pop, we could print something out. The point is, we're pushing onto the stack frame a single character. So each push operation is postponing the processing of a single character that we were not yet ready to process in some way. The stack frame that we're using in this example is designed to hold a single character. So we're pushing the letter A, pushing the B, and so forth, and here are the corresponding displays of what the stack would look like as we did our series of pushes and subsequent pops. The stack frame would be defined along this line, where we would have a character variable or a char variable. The point, though, is the stack frame is designed to hold a single character, but the processing, push and pop, is exactly what we want to do. Even if we want to process something other than character, we want to do the same processing. The thing that differs is the structure of the stack frame. So consider what happens if we said, well, we want to reverse a series of digits, effectively integers. So we get the integer digits being 1, 2, 3, and we want to effectively produce 3, 2, 1. Again, the push and the pop operations would be the same, but what we're pushing and popping is a stack frame with a different structure. It's designed to hold integer rather than char. So what we'd like to do is define this processing generally independent of what the stack frame actually looks like. That's the idea behind the generics. Now that we've provided the general idea as to how generic classes would work and how they can be created or defined within Java, let's note some restrictive behavior or some limitation with respect to these classes. When you instantiate a generic class, the type that you provide for the type parameter has to be a reference type. It cannot be a primitive type. We've made this point previously. The example that we provided did not use, nor could it use, primitive data types such as int or double. What we needed to do was to provide some implementation of integer or double, which was defined within a class of its own. That's the notion of the wrapper class. We'll have more on that in just a moment. But first, keep in mind there are two categories of data types that we want to consider. Data types such as int, double, char, and so forth are defined as being of primitive data types or built-in data types within the core language of Java. Types such as string, scanner, print writer, these are all classes. These qualify as what are called reference types. Let's explain that by looking a little bit further. When you define a variable, you specify the data type for that variable. If the data type is a primitive type, then effectively that variable gives you direct access to the value that would be stored with or assigned to that variable storage. But when you create a variable that's associated with a class, you are actually creating a variable that serves as a reference to the object that gets instantiated. So for example, when you define str as string, str becomes what's called a reference variable. The value that will be stored within the storage allocated to str will effectively be like an address or a pointer. It will be a reference to where the object actually resides. To instantiate the actual object, we use the new operator and the constructor for the class. We then take the result of that, which is the reference to where the object was located or instantiated within memory, and we can assign that to the reference variable. So in this case, str does not contain the string object, it contains a reference. Hence, string is what we call a class, but it's more appropriately called a reference type. This is the requirement for the type parameter. In addition to the notion of reference, the variables for primitive types allow us to work directly with those variables to access the storage. So if we have two integers, x and y, we can take the value stored with x, the value stored with y, multiply, add, subtract, divide, do any of the arithmetic operations directly. But recall that when we're working with an object, hence a reference variable, we use the reference variable then the dot operator to qualify a call to a method for that particular class. So str.charat, for example, or str.length. Those would be methods invoked specifically for the object to which str is currently pointing or making a reference. So the first few points on this slide all kind of summarize characteristics of reference variables. But the point is there's a key distinction between data of a primitive data type and data which is a class. So in order to use our data from primitive data types like int, double, char, and so forth, Java has defined wrapper classes. There's one class for each of the primitive data types. In addition to providing a reference to the storage, they also provide the ability to perform certain additional operations, as we'll see in just a moment. So a wrapper class is a class that is essentially wrapped around a primitive type. When an object of a wrapper class is instantiated, that object has an instance variable that stores the actual primitive value. There's a specific process that we refer to in terms of going from a primitive data type to a wrapper class and vice versa. The process of going from a value of a primitive type to an object of its associated wrapper class is sometimes referred to as boxing, and the process of going in the opposite direction is referred to as unboxing. In terms of boxing, here are a couple of examples. We say we're going to invoke integer. Remember, integer spelled this way is the class that is a wrapper class for the primitive data type of integer, and this is the constructor. So we're invoking the constructor for the integer wrapper type. The argument here is the actual primitive data type's value. So 27 is the integer that we're going to store in this object called integer object, which is an instance of the integer wrapper class. And similarly, we show how this can be done with double and character. Examples of automatic boxing are such that we don't have to provide this explicit call to the constructor. Starting with Java 5.0, the fact that the system recognizes that integer here is a wrapper class, then it will implicitly invoke the constructor for purposes of the assignment or the conversion of the value. Examples of unboxing are shown here. What we have is for each of the wrapper classes, we have something called, whatever the data type is, value. So int value, double value, char value. These methods serve to effectively extract from the wrapper class that stored value that's been embedded within an instance variable and extract that. And what we're doing in these examples is assigning the values to an actual variable of the primitive data type. So that's a little bit on working with the wrapper class. Our real goal here was to introduce the concept of the wrapper class and show you why it's important if you wanted to work with values of a primitive data type within the context of generics. There are some restrictions on the use of the type parameter within expressions that are part of the code for your generic class. For example, we say that the type parameter cannot be used in expressions where you're using the new operator to create an object. What does that mean? It means that you really cannot invoke a constructor in quite the same way that you would do it with a conventional class, a non-generic class. Here are a couple of examples that demonstrate the improper or illegal use of the type parameter. In the first case, putting t over here as the data type for this thing called an object, that's fine. There's no problem with that. It's on the other side of the expression that we have a problem. You cannot invoke a constructor using the type parameter and say, let's make a new one of whatever this thing is. So that's not permitted. In the second example, declaring ARR as an array of whatever the type parameter is, that's acceptable. However, when you invoke the new operator and use the type parameter as the data type for your array, that's kind of like invoking a constructor. So therefore, that's also not allowed. So both of these present problems in terms of the use of the type parameter. So how do we instantiate objects that involve a type parameter? That's a good question. So let's take a look at it. We need a little bit more background information. So every time I give you an explanation, I provide a little background so you better understand it rather than simply saying, do this, don't do that. So in order to understand our current dilemma here of being able to instantiate objects with a type parameter, let's first look at an issue that's associated with Java in terms of how it implements the generics. Basically, it's tied into the concept of inheritance. In Java, every class is effectively derived from a base class referred to, or an ancestor class referred to as object. So to address the issue of object instantiation involving a type parameter, you have to recognize this point first. This is all built upon the concept of inheritance, and everything effectively inherits from object. So given two classes, A and B, if we then use this thing called generic class, something like we were creating cell, suppose we created cell and popped A and B in there. So here we're just saying in general, if we create this generic class using A, and we create the generic class using B, passing those two types as type parameters, what happens is there's no direct association between classes A and B. And using them both in the generic class does not instantiate or cause a relationship to come into existence. The one thing that we know about both of them is they both have a common parent or a common ancestor of object. So this generic class with A as the type parameter is effectively derived from object. Generic class with B as the type parameter is also derived from object. That's the only similarity or association or relationship that we might consider that these two classes A and B have. If this concept is applied to our example of cell, we could say cell integer, cell string, where integer and string would be the respective A and B classes. Those instantiations simply result in this cell integer being a descendant of object and cell string also being a descendant of object. Let's look at putting this piece of background knowledge to work. To instantiate an array of a generic class is a bit tricky, but with the understanding of the inheritance that we just discussed here, that should help us solve the problem. So to declare a variable as an array, what you're doing is you would say, here's our base type, and then the square brackets to indicate there'll be a collection of values of this type. Then you have a reference variable. That simply creates the variable that can hold the reference. That does not instantiate the array. So to instantiate the array, we would then say, let's take the same type that we're dealing with. In this example, int, in square brackets to say it's a collection of integer. Let's invoke the constructor using the new operator. So here what we say is new int, and within square brackets we put some quantity to say we're going to have 5 such elements. This approach works fine as long as a primitive data type is being used. It seems logical that we should simply be able to substitute t, our type parameter, wherever we see int, but it doesn't quite work. So if we try it, let's say t, the square brackets, to say we have a collection of whatever this type is. Then we have the name of our variable. That seems fine. But the next part is where the problem resides. When we go and try to assign to that reference variable the reference that should be returned by invoking the constructor using the new operator, this is invalid syntax. What happens is we cannot use the type parameter as though it were a constructor. So this is where we get a problem. So this is an issue for us. However, remember that whatever this type is, it's a descendant of object, because everything kind of descends from object in Java. So if we were to create an array of object, this is okay. But now there's a little bit of a problem. We can create an array of object. We can create a reference variable to an array of our base type for the type parameter, but we cannot assign the reference to one data type to a reference variable that's designed to point to another data type. Just doesn't work. That's the nature of Java with their concept of being a strongly typed language. You could not have a reference variable to refer to an array of integer and instantiate an array of double and make the reference variable that you created for an integer array reference the array of double. Java will not allow that because it's strongly typed. So in this case, it doesn't work either. By creating the object array and making the reference to an array of this other type, we can't connect them. But there's a way around this. Typecasting. What we can do is we can say, let's make this array of object, and then we've got a reference variable that can point to an array of our type parameters type. And what we do is we convert the array of object, kind of treat it as an array of this type parameter. By invoking the cast operation, we get this to work. So the cast effectively achieves the type conversion to generate the actual stored values of the appropriate type from that array of object. Probably are scratching your head a little bit at this one, but this is the name of the game. This is how it works in Java. And this has to do with a couple of factors with Java, and one of them is the fact that it's strongly typed. Now, if you're not done scratching your head, keep your hand up there because you're going to do a little bit more scratching when I show you this next slide. The cast actually causes a compile warning. And this has to do with a concept in Java that's pretty important, and it's not just with Java, but it's other languages as well, as we're talking about what would be considered safe code. At this point, the compiler doesn't really know for sure what's going on here. So it's a little uncertain. So therefore, it generates a warning that said, there could be some stuff going on that I can't guarantee that it's going to work. So it's kind of being left up to you to make the call here. So what happens is, what we do is do these two operations we just described, but that results in a compiler warning. To suppress the warning, we can use this operation here, the @suppress warnings unchecked, and that will suppress the warning and we'll get a clean compile. What happens is the concept here for unchecked means that the compiler doesn't have sufficient information to determine that all type checks necessary are actually going to ensure type safety. So the IDE that you might be using would generate some kind of compiler warning to bring this fact to your attention. But this is okay. What we're doing is effectively assigning an array of null values to another array. So it's not as though we're assigning an array of apples to a pointer that can only point to oranges. We're just appeasing the compiler here by effectively suppressing that warning and saying, don't worry about it, I've got it under control. So it's a bit tricky, but that's the nature of how it works. Now, why is all of this stuff important? This is important because we want to be able to write code that can operate on a variety of different forms of data, but we don't want to have to duplicate that code. So if you're going to be taking a course in data structures or studying data structures in general, you may very well create a list of various types of things. And that list could be implemented, say, as an array. And as you create an array, you might have an array of one kind of thing. Then you'll have an array of another kind of thing, where you have a list of this first thing, you have a list of the second thing, which means that those stack frames that we talked about, hence the nodes of your list, would be structured differently. But the processing, like push and pop with the stack, would be essentially the same thing, just working on a different structure. So this is why it's important to understand this concept. So let's summarize what we've talked about. We've introduced the concept of generics in Java. We discussed the motivation for why we would use this mechanism. We presented syntax to show you how to declare a class that is generic. We declared methods in a generic class. We showed how that could be done. The point was that in both cases we're using the type parameter as a placeholder. And remember, when we're declaring the class, that type parameter is enclosed within the angle brackets. But when we're using the type parameter as a data type within the methods, we simply use the symbol, whatever it is, that identifier. We don't enclose it in the angle brackets within the methods. We also introduced the concept of wrapper classes, and we demonstrated how that played into the use of generics. And we discussed some of the restrictions with respect to generics. So hopefully with everything I've shown you, it gives you enough background that you can actually write your own generic class and work with them. This is something you will need to do in classes, say in data structures, and perhaps in practice in writing code. If you found the video to be informative, let me know. Perhaps give us a thumbs up, offer a comment. If you have any questions, because this material is a bit confusing, if you have any questions, just note those in the comments section and we'll try to respond quickly. Also, consider subscribing to the channel so you can be notified of when future videos have been posted. And once again, thanks for watching.